Friends, we continue with the study of voltage stability. In the previous lesson, we have discussed the basic concept of voltage stability, and I have discussed the transmission line characteristic. I have also talked about the VP curves for understanding the voltage stability problem. Then I discussed a problem which I shall reiterate again about the large system. Suppose for a large system, if you have to plot the VP curve, how do we plot the VP curve for a large system? Today we will specifically discuss the generator characteristics, then load characteristics, then we discuss the characteristics of reactive compensating devices such as shunt capacitors, regulated shunt compensation. Under this regulated shunt compensation, we talk about the SVC and STATCOM. We will also talk about series capacitors. We will also discuss briefly about the regulated series compensation like thyristor control series compensation and synchronous static synchronous series compensators and so on. Then we will discuss the voltage collapse phenomena, how the voltage collapse takes place in the system, what are the sequence of events that take place which may cause the voltage to collapse. Then the next point which we have to discuss is the classification of voltage stability analysis, then determination of shortest distance to instability, the continuous power flow analysis, and ultimately the prevention of voltage collapse. I intend to cover these topics in 2 lectures. The material which I am covering today and in the subsequent lecture is mainly drawn from this book on power system stability and control by Prabha Kundur. In this book, he has discussed one large system voltage stability analysis problem. The system considered is shown here. This system has 39 buses and 9 generators and 1 synchronous condenser. Now, for this system, first step is that suppose for a particular area, the area which has been identified is marked here. This is the area called as area 1. This is the area 1. Now, here in this area, some buses which are likely to suffer the voltage instability problem are identified. The buses which are very far off from the loads are like say 530, this bus number is 530. This is one typical bus which has been identified. Now, for this system, the first step which has been done is to plot the VP curves for this multi-machine system. How do we obtain the VP curve? The approach which has been considered here is that in this area 1, we increase the load in small steps. That is, at all the buses you increase the load in this area 1, and to meet this load we correspondingly increase the generation at all the generating stations in proportional to their sizes, right. And then a load flow is conducted to find out what is the voltage at this point. That is, you perform repeated load flow for different loading condition in this area to plot a VP curve. corresponding to the bus number 530. Now, this figure shows the VP curve obtained for bus 530 considering the load change in area 1. That is, area 1 has number of buses, right, and at each bus the load is increased in small steps, and to meet that load the generations also increase correspondingly, and then load flow is conducted. Then for each of the loading condition you find out what is the voltage at this bus 530, which is considered to be the critical bus and is the prone to voltage instability. Now, this curve is similar to what we have seen for a single bus system, or you can say radial transmission system, where load is at only one bus, right. Now, we can see here as the load in area 1 increases, the voltage at the bus number 530 decreases, and at this point C you will find actually that beyond this point if you want to increase the load, we are not in a position to increase the load flow will not converge, right, and therefore, we have generated actually in this example the VP curve for a 39 bus system considering a particular area and a particular bus. Now, while plotting this VP curve, the power factor at the buses, the load power factors are assumed to be constant. As when they are increasing P, you may increase correspondingly value of Q also. Now, here there are 3 points are identified. One operating point A, which is called normal operating load, which is less than 100 megawatt and more than something like 80 megawatt, around 85 megawatt is the normal load. Another point B on this curve is identified where the load is more than 160 megawatt. This point B is very close to the critical point, and C is the critical point on the system. Now, to understand the voltage collapse phenomena, one very important approach is to examine the QV curves, because we know actually that the voltage is related mainly to the reactive power injection at that buses, right. Therefore, for this system which we have examined, the QV curves are generated. Now, for generating the QV curve, the approach is that we go to this system. Let us say that we want to generate QV curve for say bus 530 QV curve. What we really do here is that we inject a certain amount of reactive power at this bus, or other way around we say that we want to maintain certain voltage at this bus, then compute what is the reactive power injection required. That is, you assume that bus number 530 is a PV bus, right, and perform the load flow analysis, and then compute what is the reactive power required at this bus to maintain the voltage at that level. Now, this exercise has been conducted for 4 different buses in this system. The buses identified are bus number 160, bus number 200, bus number 510 and bus number 530. That is, for the complete system under the normal operating condition, right, the QV curves are to be generated. Now, for generating this QV curve, again 3 different loading conditions are considered. One is corresponding to the point A, which is shown here, another is corresponding to point B, and third is corresponding to the critical point C in the system. For this, the point A, which is the normal operating condition, right, the QV curves plotted are shown here. Now, these QV curves are shown for different buses, like this is the QV curve. I will just draw it more clearly here. This is the QV curve plotted for bus number 200. Now, if you examine this QV curve, that is, on this side we have put the injected reactive power and on this side we are putting the bus voltage in per unit. Now, you can see here actually that this QV curve, if you as the bus voltage increases, initially the injected reactive power decreases. It comes to a point where we reach a minimum point. It is the minimum reactive power injection required to maintain this voltage at this level. Then to maintain the voltage at any other level beyond this point, again we have to increase the injected reactive power. Therefore, if you see this curve, then this curve is basically a V curve type thing, where when the voltage is very low, you have to inject certain amount of reactive power. If the desired voltage is more, reactive power required injection is less. Now, in this similarly this QV curves have been generated for other buses like say bus 530, bus 510, 160. All these curves have similar pattern. Now, let us examine this curve, that is the QV curve for bus number 200. This is the QV curve. Now, you can see here actually that this is the point where if you find out the slope, that is dq by dv, then this dq by dv is 0. That is, at this point the slope of the curve is 0. Now, dq by dv 0 means actually here if you increase the reactive power injection, voltage does not change, right. Now, if you go from this point onwards, then this dq by dv is positive, that is from this point, let me call this mark point, from this point onwards, then dq by dv is positive, and therefore, any operation on this part of the curve will be a stable operation, in the sense that dq by dv is positive means that when I increase the value of reactive power injected, there is an increase in the voltage at that bus. But now, if I see the left part of this curve, then the slope of this curve or slope that is dq by dv is negative. It means if you when you increase the reactive power injection, then the voltage drops, right, and therefore, this portion of the curve, of course, if I take this extended portion like this, then this portion is unstable operating point. On this portion we cannot operate, because if you just increase the reactive power, voltage drops rather than increasing. Now, this is the different type of Q curves which have been shown, and as we will see in our further discussion that the slope of this curve, or you can say the QV sensitivity, will be very important term or indicator for analyzing the voltage stability of a system. Now, this shows the QV curves generated for loading condition corresponding to B on the nose curve or on the VP curve. Now, you can examine, you can see that now the curves or the shape of the curves have drastically changed. Similarly, for the last case, that is the operating condition corresponding to the point C, again QV curves are plotted, and you can easily see that the curves have completely changed. Therefore, what we conclude here is that the QV curves for different buses depend upon the loading condition on the system, and the QV sensitivity is different at different loading condition. Now, after this let us examine the characteristics of various components of the power system which would affect the voltage stability of the system. In fact, the voltage stability depends upon the complex interaction between various components of the power system. Now, we start with the characteristic of generators. It is very well known actually that a generator is a source of reactive power. It can generate reactive power, it can absorb reactive power, and it can generate real power also. Therefore, now let us to study the generator characteristics, particularly in response to voltage stability phenomena. We see that all generators have automatic voltage regulators, and these generators or the generator AVRs are the most important means of voltage control in a power system. When we talk about the voltage control in a power system, then the devices which are available for voltage control are automatic voltage regulators of the generators, that is by regulating the excitation of the generators. We control the voltage by tape changing of the transformers. We control the voltage by reactive power injections. The reactive power may be injected by synchronous condenser or maybe by SVC or maybe by shunt compensators or static capacitors or so on, but these are the means for regulating the voltage. Therefore, in generators the AVRs will regulate the voltage. Under normal conditions, the terminal voltage of generators are maintained constants, that is, as the loading condition changes, the terminal voltage is maintained constant by the. Now, during conditions of low system voltage, because voltage stability problem comes when the system voltage becomes low, the reactive power demand on generators may exceed their field or armature current limits. This is very important point. I will explain here that whenever you increase the reactive power demand on the generator, then we have to increase the excitation current, right, and therefore, in case suppose the reactive power demand becomes such that you cross the field current limit, right. Now, the field current limit is an important limit, actually one should not violate the field current limit. Similarly, the armature current limit should not be violated. Therefore, any generator is concerned, in case suppose you come to a situation where we exceed the field or armature current limits, then we will not be in a position to regulate the voltage beyond that. Suppose the field current reaches the upper limit, it means now we will not be in a position to regulate the terminal voltage of the generator. Current limit reaches its maximum value. When reactive power output is limited, the terminal voltage is no longer maintained constant. See, in any system, the generators are very important voltage control devices, but the moment actually you reach the field current limit, then that particular generator will no more be a voltage controlling device. It will have actually fixed internal voltage, right, in which basically you are in a position to maintain a voltage which is constant behind a synchronous reactance, right. Now, to explain this point, I will just briefly talk about the operating chart of a large turbo alternator. All generators when they are operated, right, an operating chart is used, so that the operator always maintains the generator operation within the operating chart. The typical operating chart of a generator is shown here, where on this axis we have shown the reactive power supplied by the generator. That is, this is the base point. I will just highlight some lines. This is our x axis and this is the y axis. On x axis we have marked the real power output in megawatts, and y axis we mark the reactive power output in MVR. That is, this positive part of this axis shows the lagging reactive power lagging reactive power, and on this side it is the leading reactive power. The region in which the generator is to operate is confined by some considerations. One consideration is the maximum real power output, that is determined by the turbine capability. For example, here this line which is drawn here shows that this is the maximum real power output which the generator can deliver, right. Let me just draw it here. Okay. That is, this is the maximum real power output which one can generate. Then in the same mark we have in same operating chart, this portion of the curve shows, this portion of the curve shows the stator current limit. That is, in case you go beyond this side, then the stator current will be more than the rated current. Then this portion, you can see that this portion of the curve, I will show a different color here, shows basically the field current limit, right, field current limit. Then this part of the curve which is shown here is to represent the stability consideration. In fact, this graph is plotted, in fact this line, this horizontal line shows actually the situation where the phase angle between the terminal voltage and the internal voltage will become 90 degrees, and that is, we cannot operate when the power angle is more than 90 degrees, right. And this graph is plotted considering a stability margin of 10%, and therefore, the operating region is inside this graph or inside this curve which is shown here, which has we can show it 4 different segments. One segment of the curve represents the stability limit consideration, and this is basically whether operating in the leading power factor condition. This vertical line shows actually the real power output condition, that is the turbine limit. This segment Q to N is corresponding to the stator current limit, and this from N to this point N to M, it represents the field current limit, right. The moment you operate within this the generator will be regulating the terminal voltage, but the moment you reach actually the limiting condition, terminal voltage can no more be regulated, right. The next important component of the power system which affect the voltage stability is the loads and their characteristic. I have discussed actually in the previous lecture the load characteristics. There are certain loads which can be considered as a constant P and constant Q loads, that is called constant P loads. Then there are certain loads which can be characterized as a constant impedance loads. There are certain loads which can be characterized as constant current loads. And in general, load in a power system will have some component which may behave as a constant impedance load, some component may behave like constant current load, some may behave as a constant PQ load, right. Therefore, normally the composition of the load is very important and affects the voltage stability to a great extent. Load characteristics and distribution system voltage control devices are among the key factors influencing the voltage stability. That is, when I talked about the load characteristic, another important aspect which you have to understand is the voltage regulating devices in the distribution system. In any distribution system, we have some voltage regulating devices. That is, the voltage regulating devices along with the loads have a significant effect on voltage stability. Now, when I talk about the voltage control devices, one of the most important voltage control device is the under load tape changers. In the distribution system, we have under load tape changers, and as and when the terminal voltage or the voltage at the load point decreases, then this control device will try to bring the voltage to the required value or try to regulate the voltage. Therefore, the behavior of this voltage control devices and the load characteristics have a very significant effect on the voltage stability. Loads whose active and reactive components vary with voltage interact with the transmission characteristics by changing the power flow through the system. This is a very important point actually. Those who have done some studies of the power system, and if you want to account for the loads depending upon the voltage, that is load dependent voltage, I am sorry, voltage dependent loads. If you perform load flow analysis considering the voltage dependent loads, right, then the solution of the load flow will be different than a case where you consider the constant PQ loads, right, because the moment the load at a particular bus depends upon the applied voltage, then the net voltage which you get, resultant voltage will depend upon the composite characteristic of the transmission line and the load characteristic. The system voltage is settled at values determined by composite characteristic of the transmission system and the load. Now, another aspect is when the distribution voltages remain low for a few minutes. This is another interesting aspect. Where suppose due to some reason the voltage are at low level, right, then what happens is that we have many loads which are thermostat controlled. The examples are particularly even the you can say air conditioning load or the fridge, they are all thermostat controlled. Now, when the system voltage is low, right, then these devices will remain on the system for longer time to achieve the same level of temperature, right. Therefore, when a distribution voltage remains low for a few minutes, thermostats and other load regulation devices as well as manual controls tend to restore load. Restore load means actually the more loads will be there on the system. Consequently, more such devices will be operating at any given time, and this will cause further drop in voltage. More the devices are operating in the system, obviously the voltage will drop. If the voltage was low, because the low voltage devices, more devices are on the system, this in turn will cause further drop in voltage. Therefore, one has to examine the characteristic of the loads which are thermostatically controlled. Another aspect is that we have large number of induction motor loads, and the induction motors will stall at a voltage which is below 85 to 90% of the normal voltage. And suppose induction motor stalls and remains in the system, it will cause further drop in voltage. However, what happens is that most of these induction motors have magnetically operated contactors. So, that what happens, the moment the voltage is low, then the contactors will open and trip the load. When the contactors open and trip the load, the voltage will be restored again, right. Therefore, this type of phenomena takes place in the system, as voltage drops, when the load trip, voltage will again go up. For voltage stability analysis, loads need to be modeled accurately. This is a very important point actually. When I talk about the voltage stability analysis, one has to model the loads, there is industrial loads, maybe induction motor loads have to be modeled, then the thermostatically controlled loads have to be modeled. We have to model actually the operation of the under load tape changers, right. Then in addition to this, one has to model the the behavior of the shunt capacitors which are there in the distribution system for reactive power compensation. When the voltage is low, then the reactive power injected by these capacitors which are there in the system also becomes low. It is proportional to square of the voltage, right. Therefore, this whenever you examine the voltage stability problem, one has to model these loads in detail. This is very important, and the dynamics of these load models is slow. For example, actually the thermostat opens and closes, it is not very fast, it takes few seconds and even sometimes minutes, right. Therefore, when you model this, the voltage stability phenomena is to be examined over few minutes. It is not like angle stability where we examine in first few seconds, 2, 3, 4 seconds system is stable or not, that can be examined. The next important device in the power system is the reactive power compensating devices, and one has to model the behavior of the shunt capacitors, and the shunt capacitors are the most inexpensive means of providing reactive power and voltage support. That is, although we have today more sophisticated reactive power compensation devices, but the fixed shunt capacitor or switch shunt capacitor, they are the most inexpensive devices. When you use this shunt capacitors, the one very important advantage which we get is that the generator spinning reactive power is made free. That is, suppose the reactive power demand is met by shunt capacitors, naturally the generator, the demand on the generator will be reduced, so that the reactive power will have some spinning reactive power reserve, which can be used in a very short time. That is why the what used is the application of shunt capacitor will free up the spinning reactive power reserve, because generator is already operating, called spinning reactive power reserve. I already mentioned that the reactive power generated by a shunt capacitor is proportional to the square of the voltage, and during system conditions of low voltage, the very interesting part, when the system voltage is low, we want more of reactive power, but on the other hand what happens is the reactive power injected by the capacitors decrease. That is why during system conditions of low voltage, the var support drops, and thus compounding the voltage stability problem. Say the voltage becomes low, right, the capacitors further you can say reduce actually their share of reactive power, and therefore the problem gets compounded. The next category of reactive power sources come under the heading regulated shunt compensation. Under the regulated shunt compensation, we know about the static var compensators, SVCs. The another device is the STATCOM today, which is available. Then these devices, the difference between these devices is that within certain voltage, suppose we talk about SVC, I hope everybody knows about the characteristic of SVC, that in the normal voltage regulating range, the SVC will be in a position to maintain the voltage constant. But the moment you go outside this voltage regulating range, then the SVC will become a constant capacitor, a constant capacitor. It will behave like a capacitor only, just like a shunt capacitor, because it is now no more in a position to regulate actually the reactive power, right. And the reactive power consumed by the shunt capacitor is proportional to the square of the applied voltage. Therefore, that limit will become, but within the voltage control limits it maintains the voltage constant. This is very important point. Then another device is particularly the static synchronous condenser, the STATCOM and synchronous condenser. Now, the characteristic of synchronous condensers and characteristic of STATCOM are exactly identical, only difference is one is a rotating device, one is static device. But the advantage of these devices is that even when the voltage is low, they are capable of injecting reactive power, that is have an internal voltage source and this continue to supply reactive power down to relatively very low voltages. That is, if you plot actually the reactive power versus the voltage characteristic, then the state common synchronous condensers have better reactive power injecting capability, and they are fast also. The another device which is very important here is the series capacitors. When we talk about the series capacitors, we do not use series capacitors in distribution system, but we have series compensation in transmission network. The advantage of the series capacitors is that the reactive power generated by the series capacitors is proportional to the square of the current, and therefore, the series capacitors are self regulating. The reactive power supplied by series capacitor is proportional to the square of line current and is independent of bus voltage. This has a favorable effect on voltage stability. Whenever you have actually certain problem of reactive power demand being not met, because I have already talked to you that the voltage stability is the problem of insufficient reactive powers available in the system, insufficient reactive power sources, right. And particularly here, the series capacitors will be in a position to give you reactive power even if the voltage is low. Bus voltage does not depend upon, depends upon the current which is flowing, and they are very helpful actually in. Now, we will take one example of generating QV curves, because as I mentioned actually that QV curves play a very significant role, and I also mentioned actually that the voltage at a bus will depend upon the interaction between the transmission line characteristic, will depend upon the load characteristic, and will also depend upon the reactive power sources which are. Therefore, to understand the basic concepts of voltage stability, where as I mentioned that the QV sensitivity is very important, that is dq by dV, right. Therefore, here let us study how do we generate the QV curves. For this, the example consider is a transmission line supplying a load through a transformer, step down transformer. Now, the voltage V1, this is the infinite bus. The voltage of this source is assumed to remain constant, equal to 1, and its phase angle is 0 degrees, that is the voltage is 1 per unit and its phase angle is 0. The transmission line considers a long transmission line, and this example is discussed in the book on power system stability and control by Kundur in chapter 14. We will discuss the salient points of this example. At the load bus, where load is connected through a transformer, we are injecting a reactive power Qi. Qi is the reactive power which is injected at this bus. Our exercise is to plot the QV curves for fixed values of real power supplied, real and reactive power supplied. For this particular example, the loadings considered are at different levels, like say 1300, 1500, 1700 and 1900 megawatt. These are the 4 different loading conditions are considered. For each loading condition, the power factor of the load is assumed to be unity and the QV curves are generated. Now, for generating the QV curve, the approach is again what I have discussed earlier, that is to maintain a certain voltage with the given load. You perform the load flow analysis and find out what is the reactive power injection required, right. Now, this diagram shows the QV curves plotted for this example considered, Now, this graph I will again highlight it here. You see this graph. I will take this graph. This is the QV curve plotted for load equal to 1300 megawatt. On this axis we are marking the reactive power injected, and on this axis we are marking the voltage magnitude V2, that is magnitude of the voltage V2 at the load point. As we have seen, actually the graph is having the same pattern as we have seen for a multi-machine system. Similarly, you can plot curves for different loading conditions 1500, 1700, 1900. Now, on the same graph, we are plotting the characteristic of the capacitors, that is the reactive power injected by a fixed capacitor. That is, here what has been considered is that you take a capacitor whose value is say 300 MVR. It means this, what we have assumed is that there is a capacitor who we can supply a reactive power of 300 MVR when the voltage is 1 per unit, right. Now, for this capacitor, if you plot the voltage versus the reactive power injected, then this is going to be its shape is going to be parabola, right, because as the voltage increases, the reactive power increases proportional to the square of the voltage, right. Therefore, let me just take one particular characteristic. You can see this is the characteristic this is the QV characteristic of the shunt capacitor. Now, when I have already mentioned very clearly that for this, when I specify that shunt capacitor has a 300 MVR rating, means it supplies 300 MVR if the voltage across it is 1 per unit, right. Therefore, if the voltage deviates from 1, for example, this is the 1, the voltage deviates from 1, it will supply more reactive power, and when it is less, it will supply less reactive power. Therefore, this is the graph. Okay. Now, the operating point is determined by the intersection of QV curve of the load with the QV curve of the shunt capacitor. Now, this point, at this point if you see, then if you see the slope of the QV curve of the capacitor, then the slope of the QV curve of the capacitor at this intersection point is less than the slope of the QV curve of the load, right. That is, at this point is a stable point. Reason is that suppose you deviate slightly from this point, let us say that you deviate and come to this point. It means what happens? What happens that to stay at this point, it will require more reactive power, while the shunt capacitor is supplying less reactive power. Therefore, it will move and come back to A, right. However, if you take this point, then this is not a stable point, right. This can be examined. Now, a point here is that when you go from loading equal to 1300 megawatt to 1500 megawatt, you get the similar operating point. When you go to 1700 megawatt, then the characteristic of this MVR device, which is put as 675 MVR device, this becomes just tangent. But if you have an MVR device or actually the shunt capacitor whose MVR rating is 950 MVR and the load is 1900 megawatt, this is the intersection, but this point is not stable, you can examine it. What we find here is that at this point the slope of the QV curve of the system is less than the slope of the shunt capacitor. That is, if you deviate from slightly from this, you will find that voltage will keep on increasing, right. And therefore, the point which we want to highlight here is that yes, by injecting a certain amount of reactive power, we can operate the system at a stable operating point. However, if this reactive power source is of large capacity, right, then we will not be in a position to operate at a stable operating condition. Next point we want to illustrate through the same example is the effectiveness of SVC vis-a-vis the effectiveness of fixed capacitor. In this graph, we have shown the QE curves of the same system at 4 different loading conditions, 1300 megawatt, 1500 megawatt, 1700 megawatt and 1900 megawatt, 4 different loading conditions. And one typical SVC is shown here, that SVC will be in a position to maintain the voltage equal to 1 per unit. You can just see it SVC, this is the SVC characteristic shown. So far the around this voltage equal to 1 per unit depending upon slight slope, right. You will find actually that till the reactive power of the SVC is reactive power limit of the SVC is reached, it will be in a position to maintain the voltage at the same level, whether the load is 1300, if it is 1300, this will be the operating point, if it is 1500, this is the operating point, 700, this is the operating point. Now, suppose you reach at this point B, where the SVC reaches its limiting condition. The moment it reaches limiting condition, it becomes a fixed capacitor, and the capacitor SVC as a capacitive device has this characteristic as a capacitor. So, that this point B in case it is it has reached the limit, then this B again becomes a unstable operating point, because the slope of the capacitor characteristic or QV characteristic of the capacitor is more than the slope of the system QV characteristic. That is why actually we have importance of regulated reactive power sources. Right. Now, I will just take one typical scenario of voltage collapse, how the voltage collapse phenomena takes place in the system. The first we have to understand what we mean by voltage collapse. The meaning of this voltage collapse is the process by which the sequence of events accompanying voltage instability leads to low unacceptable voltage profile in a significant part of the system. This is a very general definition, that there may be certain sequence of events may take place which will lead to unacceptable voltages in the significant part of the system. When say that the voltage collapse has taken place. In fact, voltage instability and voltage collapse are considered to be the synonyms. Now, let me just explain how the voltage collapse takes place in a particular system. Suppose a system is operating. Now, in case the system is initially operating where its loading is heavy loading in the sense that actually the transmission lines are heavily loaded, we have limited reactive power sources in the system, the generators are fully loaded or generators are quite away from the source. Now, suppose a heavily loaded system is now subjected to some sort of contingency. Now, example of contingency may be that there is one heavily loaded transmission line is tripped. The moment this happens, the other lines will be further loaded and the reactive power consumed by these lines will increase, and this will cause reduction in voltage. Now, when the reduction in voltage comes, the immediate thing which will happen is that the underload tape changers will come into operation to retain the voltage, and in case actually the ULTC in a position to stop the voltage drop, voltage will be at a certain level. Voltage drop, suppose the voltage is dropping and the ULTC start functioning and the voltage drop is stopped. Another thing which happens is that suppose the ULTCs reach their limits, then they will not be in a position to regulate the voltage further. There is a possibility that generators may also reach the field current limits. They are not in a position to further supply the reactive power. This will cause naturally the reduction in voltage, because earlier generators were in a position to maintain the terminal voltage, but the moment actually the reactive power demand has increased, they reach the reactive power demand, and therefore, the moment reactive power demand limit is reached or reactive power limit of the generators is reached, then they will no more be regulating the terminal voltage. Then the effectiveness of the shunt capacitors have reduced, because when the voltage is low, shunt capacitors supply less of reactive power, and all these phenomena put together may cause the system to lose the voltage stability. Although sometimes what happens is that when the voltage drops, then some of the loads start consuming less power, because the power consumed by the loads depends upon the voltage. When they consume less power, right, there is a possibility that the system will stabilize to a low voltage, but at the acceptable level. Voltage may be low, but it is acceptable level. But the sequence of events that take place in a very complex manner, right, and in that whole process if the reactive power sources are weak, we have less of reactive power, then voltage may come down to a very low level, and we say it is a voltage collapse phenomena. Now, for studying the voltage stability, we always divide this stability phenomena as a large disturbance voltage stability phenomena and small disturbance voltage stability phenomena. This classification is similar to that for angle stability. We just define the large disturbance voltage stability. The large disturbance voltage stability is concerned with a system's ability to control voltages following large disturbances such as faults, loss of load or loss of generation, or a loss of heavy loaded transmission lines, right. That they are called large disturbances, similar to our angle stability problem. We will discuss actually the large disturbance voltage stability analysis in the next lecture. I will talk about the modeling requirement, other requirements when we study the large stability problem. The determination of this form of stability requires the examination of dynamic performance of system over a period of time sufficient to capture interaction of such devices as ULTCs and generator field current limiters. Large disturbance stability can be studied by using non-linear time domain simulation, which include proper modeling. In fact, actually the angle stability and voltage stability, the mathematical model required is identical, except that certain details which are necessary for voltage stability may not be relevant for angle stability. Small disturbance voltage stability, the small disturbance voltage stability is concerned with a system's ability to control voltages following small disturbances, such as gradual changes in the load. Whenever we talk about small disturbances, means gradual changes in the load. Idea here is that the system is never in static condition, it is always in quasi static condition, loads keeps on changing, and when the loads keeps on changing, right, then if we are in a position to control the voltage with the small changes in load, we say the system is small signal voltage stable. With this let me sum up what we have discussed today. We have primarily discussed two important aspects. One is how to generate the cubic curves for a system. I have given the example of generation of cubic curves for a large system. We have also plotted the cubic curve of a machine infinite bus system or a load connected to a long transmission line. We have also seen the interaction between the cubic characteristics of the system with the cubic characteristics of the shunt regulating devices like fixed capacitors and actually regulated static watt devices. I have also defined the voltage stability as small signal voltage stability and large signal voltage stability. I have also briefly mentioned about the voltage collapse phenomena, how the voltage collapse takes place in the system. We will continue with this in the next lecture. Thank you.